We're going to start with a quick review of forces. And to do that, I wanted to start with a couple of conceptual problems. So let's say we define, per usual, the positive x direction being to the right. I've got a 10 kilogram block that's being pushed to the right at a constant speed of 10 meters per second. Is the net force on the block positive, negative, or zero? Well, here's what we know. We know that if I sum up the forces on the block, this would be our net force. That has to equal the mass times the acceleration. Recall that the acceleration tells me how the velocity changes over time. But we have said that the velocity is a constant 10 meters per second. Therefore, this is zero. Therefore, the net force must also have to be zero. There's got to be no net force if the object is not accelerating. If it's not accelerating, it cannot have a net force, even though the object is moving. If I have a force, the object has to be accelerating. We have two blocks here, block A and block B, and you are pushing on the blocks, you're pushing them to the right. So the blocks are sliding to the right. And then the question is, what is a bigger force? The force of block A on B, or the force of block B on A? Is it that the force of A on B is greater? The force of block B on block A is greater? Or is it that the two forces are equal? Okay, well, if we look at this, we can see that if B is being accelerated this way, there has to be a force of A on B. And by Newton's third law, there has to be an equal and opposite force of B on A. So if we're talking about the magnitudes of the forces, the force of A on B has to be exactly the same size as the force of B on A. Same situation, but now the question is slightly different. I want to know what's bigger, the force of block A on block B, as you push the blocks to the right, or the force of you pushing on block A. Which is bigger? Is it the force of A on B is bigger? The force of you on block A is bigger? Or are they the same force? Well, we can see that you are pushing on block A directly. But because you're pushing on block A, block B is also moving. In fact, we can, depending on how we define our system, we can define A and B to be the whole part of one big system. And in that case, it must be true that the force that goes into accelerating this big mass has to be bigger than the force accelerating just this little block B. So it must be true that the force of you on block A is bigger than the force of block A on block B. The reason being is that if the two blocks are going to have the same acceleration. And for that reason, A is going to have a larger force pushing to the right. Since it has more mass, it will take a bigger force to accelerate it at the same rate. Not to mention the fact that A also feels this backwards force from block B on block A. So that means you're going to have an even bigger force pushing on block A in order to get it to accelerate at the same rate as block B. Let's review how to solve force problems mathematically as we did last semester. We'll start with one-dimensional forces, and from that we'll build up to two-dimensional forces. So suppose we have a mass of 5 kilograms and a force of 10 newtons that is being used to pull on that mass. We want to know what is the acceleration of the block. Well, we've already done step one, which is draw a picture. And in fact, we've done step two as well, which was to make a free body diagram. Picture, and we've made a free body diagram. The next step for our solving forces problem was to sum up the forces and set that equal to the mass times the acceleration. In this case, I'm using a fairly simple problem. There's only one force, but we can sum up those forces to make that equal to the mass times the acceleration. We would say that the force equals the mass, which is 5 kilograms, times the acceleration, which we want to find. We would say that the acceleration is the force divided by the mass, which in this case is 10 newtons, divided by 5 kilograms, giving us a force, or excuse me, an acceleration of 2 meters per second squared. So using these steps, you should be able to figure out how to solve any force problem. Now we're going to extend these steps to force problems in more than one dimension. For two-dimensional force problems, we again are going to follow a series of steps that will lead us to an answer. And there's a few more steps for solving two-dimensional force problems than there were in one-dimensional force problems. But essentially what we're going to do is, much like we did with two-dimensional motion problems, two-dimensional kinematic problems, we are going to change the problem into two one-dimensional force problems. We're going to change it into two one-dimensional problems. Since we already know how to solve force problems in one dimension, if we can convert it to a one-dimensional problem, it'll just be the same, it'll just be a little bit more work. So here we go. First thing, draw a picture. So let's say you have, again, some ramp, and there is a block on the ramp. Okay? Step one, we've drawn our picture. Step two, we want to define our coordinate system. Well, we've already seen blocks on a ramp problem before. And what we did last time is we put our coordinate system along the ramp at an angle so that the x-axis was parallel to the ramp and the y-axis was perpendicular to it. And that's a perfectly good coordinate system to use. So I'm going to stick with that coordinate system. Okay, so we've done that. We've defined the coordinate system for x and y. The next thing we want to do is draw our free body diagram, our force diagram. I want to know what are the forces on that block. Well, I know gravity is pulling it down. And since it's not falling through the ramp, there's got to be some force preventing it from doing so, and that's got to be the normal force. Which I'll write this way, as the normal force on the ramp. And there may be other forces in here as well. Maybe there's some strings, so maybe there's some tension on the block. Maybe there's a spring pushing it up. Maybe there's some friction. But for now, I'm just going to keep it fairly simple. Let's say it's a frictionless ramp, so not a significant amount of friction, and the block is just sliding down the ramp. So those two forces. We've drawn our free body diagram. We're already through 3 steps. Next, we would want to break our vectors into components. So what we can say is, let's, just don't want to do that yet. Let's write our normal force first, since that's easy to do. Well, the normal force points all along the y direction, so it has no component in the x direction, but a magnitude Fn, which points all along the y direction, positive y direction. The force of gravity is going to be trickier. To do that, I have to know what the angle of the ramp is. And we've seen a problem like this before, where we had that angle of the ramp, and we said that the x component of that gravitational vector, we actually looked at the acceleration of gravity rather than the force of gravity. But since they both point in the same direction, the math is going to be almost exactly identical. But what we can say is that the force of gravity is going to be, let's see, it'll be mg, but some of it points in the x direction. And we showed before that that was going to be given by the sine of theta. And for along the y direction, it would be mg, if you work out the geometry, times the cosine of theta. You can figure that out using SOHCAHTOA and similar triangles based on the direction of the force of gravity. So I know this. We've broken our vectors into components. Now I want to look at what the force is doing in each of those different directions. So we're going to sum up the forces. But we're in 2 dimensions now, so we have to sum up the forces twice. What that means is, I'm going to sum up the forces in the x direction, and I'm going to sum up the forces in the y direction. When I sum up the forces in the x direction, I am going to get the mass times the acceleration in the x direction. And when I sum up the forces in the y direction, I'm going to get the mass times the acceleration in the y direction. Well, we can do that pretty easily. I'm just going to add up the x forces. That just equals negative mg sine theta from the force of gravity, but nothing from the normal force. That'll be negative mg sine theta. And in the y direction, that'll be, I'm going to write it down here so I have a bit more room, the normal force, which is pointing up. This should have been minus because the gravitational force is pointing in the negative y direction. So that'll be minus mg times the cosine of theta. Now we can tell automatically from this that the acceleration in the y direction has to be 0. Why does that acceleration have to be 0? Well, the block is not moving up and down off the ramp, it's just staying on the ramp. Therefore, the acceleration in that direction has to be 0. But that means, if this side has to equal 0, it's got to mean that the normal force is equal to mg cosine theta. So we found a way to figure out what the normal force is. From this side, I look over here. I've got this equation. The masses cancel. So I can figure out the acceleration in the x direction. Now once I have that acceleration, I can figure out lots of things. I can figure out, I can use my kinematics equation to determine how much time it's going to take to fall down the ramp. If I tell you how much time it's going to take, I can tell you the length of the ramp. Once we do this, we can figure out lots of other quantities using the kinematics equations that we've gone over. But in general, this is how we're going to solve force problems. It's fairly straightforward. We just want to follow these steps. Draw a picture. That's easy enough. Define your coordinate system. Draw your free body diagrams. If you get your all the forces that are in the problem, and you put them all in the right direction, your free body diagram should go fine. You want to break your vectors into components. That's a little bit new. That could be tricky. But it's really just a matter of thinking about SOHCAHTOA and doing trigonometry on your vectors. And then finally, summing the forces. Once we get to this part of the problem, this is just the same one-dimensional force problems that we've been working with since the last semester. So if you follow these steps, you should be able to solve just about any force problem that we're going to see in the course. Let's do an example showing how to solve force problems in 2 dimensions. So I have here a block. The block has a mass 10 kilograms. And we are pulling with some force that I will call F pull. So you can imagine maybe this is a suitcase that we're dragging along. And we're pulling with some force F pull. And we're pulling at an angle theta, which is going to be 45 degrees. And there is some frictional force pulling back on the suitcase or the block, whatever it happens to be. And that force of friction is going to be 2 newtons. Now, we want to go through all of the different steps for solving force problems. And we've already done step 1. We've drawn a picture. Next thing I want to do is define a coordinate system. So I'm just going to do that off to the side here. I'm going to say to the right is the x direction, and up is the y direction. So I've defined my coordinate system. Now I want to make a free body diagram. So I know already that there's a force F pull. Really, I should put a vector hat on there because it's a vector. Pulling up and to the right. There's some force of gravity, which is equal to mg, pulling down. Let's see. There's a normal force, which I will call Fn, pulling up. And then finally, there's the force of friction pulling back. Now, I want to figure out what's the acceleration of my block. Now, let's assume that the force I'm pulling with is not enough to overcome gravity, so that the block doesn't just come jumping off the ground. We're going to be dragging it along the ground. So really, I'm mostly going to be interested in the forces in the x direction. So what I want to do next is since I'm going to be interested in the forces in the x direction, I want to break all of my forces into their x and y components. Now that's pretty easy for most of the forces. So the force of friction is only along the horizontal, so that's only going to be in the negative x direction. The normal force and the gravitational force are both completely vertical, so they are going to be only along the y direction, positive or negative y direction. But the force that I'm pulling with, that's a force that can be broken into its x and y components. So what I'm going to do is look for the x component of the pull force, which I will call Fpx, and the y component of the pulling force, which I will call Fpy. So F pull can be broken into 2 components, one that pulls along the x direction, one that pulls along the y direction. And I can use SOHCAHTOA to figure out what each of those different components are. And it's not very hard. All I have to do is say that F pull in the x direction is just equal to F pull times either a cosine or a sine. And if I look at this angle in this x direction, I can see that the x direction, the x component of that vector is adjacent. So that would have to be cosine by SOHCAHTOA. And I can do the same thing for the y direction, for Fpy, which this time is opposite to that angle. So we would say Fpy equals F pull times the sine of theta. So we've broken our vectors into components. I now know the different components of my pulling force. I'm free to move on in solving the problem. So we've done our free body diagram, we've broken into components. Now I want to sum up the forces in the x and y directions. We'll do that over here. Let's do the forces in the y direction first. let's see, there is a normal force, there's the force of gravity, and then there is the y component of my pull force. So that would be Fn minus the force of gravity, minus because it's going down, plus Fpx. That would have to equal, or sorry, excuse me, Fpy. And that would have to equal the mass times the acceleration in the y direction. In this case, we know it's not leaving the ground, so this would have to be 0. So that's how we would sum up the forces in the y direction. I just look at all of the forces that point straight up and down, and I sum them up. But we're actually interested in the acceleration, which is only going to be along the x direction. So what we want to do, the more relevant information for us, is summing the forces in the x direction. And we can see here that those forces would be, let's see, there's a minus from the force of friction, negative force there. And then there's the x component of the force that you're pulling with. So it would be plus Fpx. That would have to equal the mass times the acceleration in the x direction. We can rewrite this equation as minus the force of friction plus Fpx, but we know Fpx is the pulling force times the cosine of theta, has to equal the mass times the acceleration. From this, we should have enough information to solve now, because I know that the force of friction gives a 2 Newton force. The pulling force gives a 10 Newton force. We're pulling at an angle theta, which is 45 degrees. And we have a mass, which we said was 10 kilograms. So the only thing we do not know is that x acceleration, which is what we want to solve for. So all I have to do is divide by the 10 kilograms over here. Plug in all of my numbers on the left-hand side, and we will get the acceleration in the x direction. In this case, the acceleration in the x direction is just going to be given by, assuming I did my math correctly, 0.51 meters per second squared. Once I have that acceleration, I can do other things. I can look at the kinematics. I could look at where the block is going to be at different times. I can do any sort of kinematic problem once I have that information. So the take-home message is, if you follow the steps for doing two-dimensional force problems, draw your picture, make your free body diagram, break it into components, choose your coordinate system. If you do all of those steps, you should have no trouble solving just about any force problem I throw at you.